Yeah, can you talk to me after the class? Yeah. All right. We talk about how to represent single particle operators in the second quantization picture. And here, the single particle operator basically means it's only regarding a single particle's property, but because we have a system of identical particles, then this single particle operator is actually going to act on all the particles. So it effectively becomes a sum of the individual particle's property. Right? So when you're doing that, what we find is that the single particle operator, we denoted by this curly A here, is just going to be represented by a sum over L, L prime, and then we have A, L, L prime, and AL dagger, AL prime. And here the AL dagger means we are creating a particle in the basis state by L. Right. So suppose if you only have one particle in the system, then we can always define a basis for that single particle's Hilbert space, and those are called the phi L's. And then this ALL prime is basically the matrix element of the single particle observable A. In this phi L basis. Right. And this curly A here is basically a sum of these single particle observables for each different particle. And if you're actually using the eigenbasis for this operator A here, so suppose so if let's say usually we use per psi k just to not confuse you. If this is the eigenbasis of A, so basically these per psi k's are eigenvectors of this operator A here, and we are going to assume A here is Hermitian. So then these eigenvectors will always form the basis of the Hilbert space. In this case, this expression simplifies to just a sum over k of lambda k. So to not confuse you, let me use ck dagger ck. So it's just a special case of the equation above, but I use a slightly different notations here. And here the lambda k's are the eigenvalues of A. Right, and an intuitive way to understand this is to treat A as, for example, the Hamiltonian of your system, and then the eigenvalues of the Hamiltonian are basically the eigenenergies, and this equation is basically the sum of the total energy, because this ck dagger ck is the same as nk, so this basically counts the number of particles in the energy eigenstate k, and the energy is given by lambda k. So when you do a sum of nk and lambda k, that gives you the total energy of the system. Right. Okay, so that's kind of a review of what we learned in the last class. And today we're going to get more complicated than this. We're going to look at two-particle operators. And interactions. And this is also where things get more interesting, because if you're only looking at single particle operators, you're only considering the properties of individual particles, and then interactions are not basically playing the role. So this cannot capture any operator that describes the interactions between two or more particles. So we're going to here focus on operators that represent interactions of two particles. And as we said earlier, these actually are the majority of physical interactions between particles. Most physical interactions are pairwise, so the interaction energy only depends on the property of a pair of particles. Usually only two particles interact at a time. Of course, you can have many particles, each two will interact, but the interaction only concerns two particle operators. For example, we can consider the Coulomb interaction as an example. between two charged particles. Suppose we have two particles, I and j. So they have position xi and xj. Then the Coulomb interaction is basically given by some function of xi and xj. Right. And of course, here the xi and xj should be operators. This is what we learn in undergraduate quantum mechanics, right? All the positions should be given by position operators. But I'm not going to put hat on it just for simplicity. Then the question is, so suppose we have n, identical particles. And then the total Coulomb interaction energy, so it's a total interaction energy, or we can also say the interaction Hamiltonian, because the energy and Hamiltonian are basically synonymous. So this is going to be given by, let's use a curly V here as our standard notation. The curly ones will correspond to the many-body version, which is the sum of these interaction energy for each pair of particles. So we sum over all the I and j, and then we take this V, xi, xj here. Right. So this is what we would do in the first quantization picture. Like in undergraduate quantum mechanics, this is how you represent the total interaction energy for n particles. They have these pairwise interaction energy. So the idea for going into the second quantization is we want to write everything in terms of the creation and annihilation operator. And so this is also how you basically know whether you are using second quantization representation. If you actually see all the operators are written as functions of creation and annihilation operator, that means you are in the second quantization picture. And if you look at the state, if the state is actually represented using the basis, this many-body Fock basis state, this N1, N2, that also means you are using second quantization picture. So that's kind of the notation we are using. So how do we do this? So this is actually not very hard, because here we see that this is a potential energy. This is an interaction energy between two particles and xi and xj. And first we can use the position basis. So the position basis we know is just given by these ket of x, where x just denote a particle at a particular position x, right? And whenever we are talking about this basis, this is a single particle basis. This is the same as this, per psi, phi L or per psi k here, right? So this is a single particle basis. Assuming you only have one particle, what is the basis you want to choose? And in this case, we choose the position basis. Later, we're going to choose momentum basis, but let's start with just the position basis. And then you can define your creation operator in this basis. So we can call it Cx dagger, which basically means it creates a particle in this basis state x, which also means create a particle at position x, right? Because this is a definition of the position basis. It just denotes a particle exactly at position x. It's a basis state, right? Because apparently if x is different, those states are orthogonal. The particle cannot be, right? If it's not a superposition state, it can only be at one position at a time. So that Cx dagger basically denotes this. And then if you look at this quantity here, you can actually show that this V here is going to be given by 1/2 of sum over x and x prime. Then we have this potential energy x prime, and then we have Cx dagger, Cx prime dagger, Cx prime, and Cx. So this looks a bit complicated. I'll try to make more sense of this. So you can see, just intuitively, this is like I remove two particles at position x and x prime, and then I create two particles at position x prime and x. So at the end of the day, I'm really not removing or adding any particle in the system. So and the way you think about this is kind of close. So if x is not equal to x prime, this one actually can be So the 1/2 here, is actually just to take into consideration that this sum is over x and x prime, and typically here we would assume that I is smaller than j. It's really just a convention here. So you could also just, assuming this summation is over all the I not equal to j, and then put a 1/2. Of sum I not equal to j be xi xj. Right? Because the summation here can be either I smaller than j or I larger than j. And because this potential energy typically is symmetric, right? Because if you exchange the two particles position, it's the same. So for example, for the Coulomb interaction energy, we know it's just equal to q squared divided by xi minus xj, the distance between the two. So apparently it's symmetric under the exchange of the xi and xj. So as long as you have that, you can put a 1/2 and then sum over all the I not equal to j, or you can just do I smaller than j. So either way would work. All right, so now about this part. So let's first look at the case when x is not equal to x prime. If x is not equal to x prime, question, Richard.
You just answered it, actually, sorry.
Yeah, go ahead, John.
Is the order that you create and destroy?
Yeah, it matters. I'm going to get there. Yeah, so the order actually matters. If x is not equal to x prime, we can actually move these things around a little bit. So I'm going to change this to cx dagger cx and cx prime dagger cx prime. So what I need to do is to move this operator cx first here and then here, right? So I'm going to move this operator 2 times. So first I'm going to swap these two, and then it's going to come here, and then I'm going to swap these two, and it's going to come here, right? So I'm going to exchange it twice. And no matter whether it's bosonic or fermionic, right? No matter whether we are dealing with bosons or fermions, if you exchange twice, you always get the same thing, right? So this is going to exactly give you this part, right? So these two are exactly equal. And this one is not hard to understand. It's just nx prime. Right, question, Richard.
What was the significance of the x not being equal to x prime?
Yeah, so here we're assuming the two particles are not on the same side, right? So that's the meaning. I'm going to come to the case when x is equal to x prime, just in a moment. Yeah.
Just because those commute.
Yeah, those commute. Well, yeah, in principle, the x, so these two can anti-commute if they're fermion, but I swap it twice, so it doesn't really matter, right? Now, once it becomes n, that becomes simple. So when you have nx and nx prime, what does it mean? Yeah, question.
Yesterday, when we were working through one of the questions, there was a point where instead of swapping multiple times, we said we could just swap two that were further apart.
Yeah.
When can we do that, and when can we not do that?
You can always do that, but it's not going to give you exactly this, right? For example, if you want to swap this and this, yeah, so cx is going to come here, but the rest of them become cx prime and cx prime dagger. So it's the opposite of this. So you still need to swap it twice. So you can do it in different ways, but you always need to swap twice in order to get to the bottom expression, right? Yeah, you can swap any two fermionic operator. Okay, so then we have this nx prime. So that basically just count how many particles are in the position x and in the position x prime. So this is actually, directly related to the fact that we have interaction energy like this, right? So let me highlight this part. So if you look at the interaction energy like this, and you are summing over all the I and j pairs, so this expression here exactly represent that. If you think about this, it's a sum over this, right? So the summation should be in the front as well. So if I write this fully, so this basically means V, sorry. My V here is a sum, so 1/2, this is x not equal to x prime, then I basically just have nx prime, V x prime, right? So I'm basically counting how many particles at position x and how many particles at position x prime. And then I have this potential energy, right? So this is, again, kind of the same as what we said early on, right? When we are thinking about this, you can think about it as the total energy. And here, this is the interaction energy. And then we need to count how many particles at x and how many particles at x prime, right? The simple example is that I have exactly one particle at x and one particle at x prime. In that case, both of this is equal to 1, and then you're exactly just representing the interaction energy of these two particles, one an x and x prime, right? If I have multiple particles, then you basically just multiply them by nx and nx prime, right? Yeah, yeah.
So if it can if it can commute or anti-commute either way in this scenario, does the x not equaling x prime matter in this specific scenario? Or
In this case, it doesn't really matter because I'm swapping twice. Whether it's bosons or fermions doesn't really matter. For fermions, I'm going to come to that very soon. If x is equal to x prime, you actually cannot, right, have two particles at the same time. So I'm going to come to that. Yeah.
Is this operator purely on diagonal? Because if I remember correctly, the number operator is on the diagonal.
Yeah, it is diagonal. Yeah, so you're right. So that's a good point too. So in this case, this operator is actually diagonal in this position basis x, right? Because I'm choosing the basis that makes it diagonal. It sort of makes sense because if you're looking at my interaction energy, I'm also writing it in the position basis, right? So it's just given by Vxij. So then once you do the second quantization picture, it is also diagonal. So it's just nx prime. But it's no longer quadratic. That's the important thing. So if you write this as creation and annihilation operator, you see that it's actually quadratic. Well, compared to the single particle case, you are either getting something like this or you are just getting this, right? So it's going to be quadratic. Quadratic basically means it's a quadratic in the creation and annihilation operators. So once you have interactions, this becomes quadratic. Okay, so because the interaction energy depends on the number of particles at these two positions, we also call this density interaction because this nx here, you can think about it as the density of the particle at position x, right? So this is sometimes also called density interaction. So basically, the interaction depends on how many particles you have at each position. Okay, so now let's look at the x equal to x prime case. I know some of you are already curious about that. So for x equals to x prime, this actually allows us to see why we have to have this particular order here, right? So why do we need to have this sort of weird order? We have two annihilation operators on the right and two creation operators on the left. And this actually takes care of fermions on the lattice. So, so first, let's look at the boson case. So for the boson case, this actually exactly simplifies to this because for bosons, these creation and annihilation operators actually always commute. So you can still do this swap, right? So the CX, so even if x is equal to x prime, so actually let's do this. So explicitly, so we have Cx dagger Cx. Actually, they're not exactly the same, but they're close to that. So it looks like this, right? So this is for x equals to x prime. And then we're going to use the commutation relation. So what we're going to do is to, let's see. So how do we do this? So we can move this one to the left. So then we have to use the commutator. So this becomes, we have to use the fact that Cx and the Cx dagger is equal to 1. So then this means Cx dagger minus Cx dagger, Cx is equal to 1. So that also means Cx dagger Cx is equal to Cx dagger minus 1, right? So now I'm going to basically use this right here. So this is the equation I'm going to plug in. So this becomes Cx dagger minus 1 Cx, right? I'm going to expand this. So this becomes Cx dagger Cx dagger Cx minus Cx dagger Cx. Okay, so Cx dagger Cx is equal to nx, and that's another nx, so I get nx squared, and then minus nx. And the other way to write it is this is equal to Cx nx minus 1. Right. So for bosons, this actually simplifies to nx minus 1. And then let's look at the fermions. We'll talk about what these terms actually mean just in a moment. Let's first do the algebra. So for the fermions, actually you don't need to do anything. This is directly equal to 0. Why? Because Cx, we have 2 Cx here, and we know Cx squared is equal to 0. Because for fermions, you can't actually remove two particles. So there can never be two particles in the system, right? If you can only have at most one particle, and if you remove one particle, it goes to 0 particle. If you try to remove another one, it kills the state, right? So it's impossible to do that. So Cx squared is already equal to 0. That also comes from the anti-commutation relation we talked about in the previous class. So this is equal to 0, so which also means Cx squared is equal to 0, right? So this anti-commutator is just 2 times Cx squared. Okay, so for fermions, you just cannot have two particles at the same position because you have this particular form of the interaction. And for bosons, it's equal to nx minus 1. So why do we have a form like this? If you think about this, this term is actually going to be a 0 if nx equal to 0 or nx is equal to 1, right? But starting with nx equals to 2, you can actually have this term is non-zero. And this makes intuitive sense because when we are thinking about x equals to x prime, and you still want to quantify the interaction energy, you have to have at least two particles at that same position. If you have 0 particle or you have 1 particle, you should not have any interaction energy, right? Because the interaction energy is between 2 particles. And this term exactly represents that. You have to have at least 2 particles at that position in order to actually have a non-zero interaction energy. And this particular form is called the on-site interaction. It's basically like you have 2 particles at the same site, at the same position. And then you are going to basically have an interaction that looks like this. So now if we go back to this expression, you can actually see this expression makes perfect sense. So if you think about the x equals to x prime case, then in the bosons and fermions, they both make sense. For fermions, you should get 0 just because you can't have 2 fermions at the same site. And for the bosons, you actually will get this term, which also makes sense because you need at least nx equals to 2 to have 2 particles interacting on the same site. And this is also the reason why this 4-body operator has to take this particular form, right? For example, if you write it as sort of a more convenient form here, let me just write it here. So what if the interaction actually looks like Cx dagger, Cx, and then Cx prime dagger, Cx prime, which means it's exactly equal to nx prime. So that would be the classical way of thinking about this problem, right? So since we have, the interactions between 2 particles, why don't we just directly have nx and nx prime? That's an intuitive way to think about it, right? But immediately you are going to run into issues because what if if x is equal to x prime, this becomes nx squared. So what if I just have 1 particle there? And this will still give me a interaction energy that is non-zero, right? It's just equal to 1. And that doesn't make sense because you only have 1 particle at that position. How could you even have an interaction energy? And the particular reason why we're taking this order is just because it ensures that we have no interaction energy when we only have 1 particle at that position. Yep. Any questions? Okay. So with this type of interaction, you can already explain some very interesting models. So in the last class, we talked about this Hubbard model. And the Hubbard model actually is just made of interactions like this. So interactions like this nx, nx minus 1. Suppose we just have interactions on the same site. This is sometimes called, so let me actually write the full thing here. Let's call this Bose-Hubbard model. So suppose we have bosons, then the Hamiltonian will be given by something like this. So we have a sum over, so in the last class we talked about the tight binding model. So we have something like I and j, and then we have some Tij, Ai dagger, Aj. And then you have terms that are similar to this, so let's just make a u here, and then sum over I of ni minus 1. So I'm putting it on the lattice, but it's very similar to this. You don't necessarily need to put it on the lattice. But putting on the lattice, I'm just going to replace x by I, because I here will label the position of the atoms because it's on a lattice. It's discrete, so x position, the position x can only be at discrete values labeled by I. And then if I just change that on-site interaction to this and put some coefficient, let's just call it u here. And also, just for simplicity, I'm going to just call the hopping strength T. It doesn't have dependence on I and j, it's uniform. And this is a nearest neighbor. And this particular model is just called the Bose-Hubbard model. So this is for the bosons, because for fermions, we can't even have on-site interaction. That term just goes to 0, right? We just can't have two particles on the same site. So this Bose-Hubbard model is already a very important model, and it's actually the first model physicists managed to use quantum simulators to simulate it. It's a simplistic model. We can't actually find it in a natural material. So you can only sort of use quantum simulation to actually realize this Hamiltonian. And the achievement of simulating this model is actually made by Emmanuel Bloch's group I think it's about 10 years, maybe it's probably 15 years ago, at this point. And I showed you this video made by Emmanuel Bloch, I think it's 2 weeks ago. And he basically led this effort, and it's a huge achievement. You can actually simulate a phase transition in this model. And we're going to talk about phase transitions later, but just to give you a brief idea. So you have two parameters t and u here. There are actually two different limits here. So if t is much smaller than u, suppose this on-site interaction energy actually dominate, and then you are going to get to a phase called the mod insulator. And then when t is much larger than u, you're going to get a superfluid phase. I can give you a brief picture of what these two phases actually mean. So when this energy dominates, what happens is that you cannot, so we're talking about the ground state or the low temperature state here, because that's where things get quantum. So if you look at the lowest energy state, then you don't actually want to have two particles at the same site, right? You don't want to have two particles on the same site because in that case, this interaction will be larger than 0, right? If U is very large, and that's going to be unfavorable. Instead, you want to have exactly one particle per site. Question, Richard.
What is the T's much less than U case called?
T much, sorry, what's your question?
I can't read what the T much less than U case is.
It's called the mod insulator. Yeah, it's called a mod insulator. So what happens is you have exactly one particle at one lattice site, right? So because you don't want Ni to equal to 2. So Ni can be either 0 or 1, right? So either you have no particles there or you have one particle there. And the particles don't move, right? Because if they move, you could have two particles on the same side. That is kind of exactly as an insulator because these particles don't move. But it's not like the insulator you think about for like metal or insulator. It's a different type of insulator. So the insulator you think about, like one that doesn't conduct electricity, that's called a metal insulator. And this is called a mod insulator. It's a little bit different. It's basically like the particles are not moving. For the metal insulator, for the actual insulator you think about in everyday life, it's not insulating not because the particles are not moving, it's because there's like an energy gap. So the particles just don't have enough energy to move to the other band, which is called the conduction band. Question, Kobe.
Is U positive in this case?
Yes, in this case, U is positive. Yeah, so we are looking at the positive case. The negative case will be totally different. So the positive case basically means the particles are repulsive. If you put two particles on the same side, you have to pay a positive energy. So we're always looking at the positive case. The negative case will be pathological in the sense that you can put all the particles there. Yeah.
Wait, I'm a bit confused. If U is really large
Yeah.
versus T, wouldn't there be more particles in the same?
No, because you want to lower the energy of the system. If U is positive and you want to find the lowest energy, the ground state of the system, you want to minimize that second term, right? You want to minimize this one. And then the Ni should be as small as possible. Ni is an integer, so it can be either 0 or 1 as the smallest, right? And that will both make this term 0. So you don't want Ni to be equal to 2, right? Or beyond. And then there's this other regime where T is much larger than U. You can think about the case is just you turn off U. There's no interaction. You just have this first term. And this term will give you a phase which is called the superfluid. I can't explain the details at this moment, but we're going to get to that very soon. We're going to actually solve this first term analytically, and you'll see why it's called a superfluid. But the basic idea is that the particle kind of just does not get localized, and you can actually get an extensive wave function. The particles can be anywhere. So that's basically the idea. That's called a superfluid. It's very different from the model insulator where the particles just don't move. And then you can see that if I tune this ratio of T over U, then I'm actually going to get a transition between these two very different phases. Right? One is that the particles can be everywhere. The other one is the particles just sit on their own lattice side and not moving. And there got to be a phase transition between the two. And that phase transition was actually first observed experimentally using quantum simulation. And of course, we can also have a fermionic version of this. So the fermionic version, the first term will look the same. But the second term, of course, will be different because we can't actually have on-site interaction, so that will strictly become 0, as we said. The other way to think about it is, for the fermions, Ni can be either 0 and 1, so that term is already 0. For the fermions, you have to think about interactions which are on different neighbors. So in this case, the interaction will look like Ni and Ni plus 1. So why I only include the pairs that are neighboring? So that's again this tight binding approximation we talked about before, right? We're going to assume that if these particles are further apart, their wave functions are going to have very small overlap, which makes any energy, interaction energy negligible, which sort of also makes sense, right? If you have interaction energy that decays as distance, you probably only want to include the neighbors. But of course, in real materials, the electrons' interaction energy can be Coulomb-like, which only decays as 1 over the distance. In that case, you have to include more neighbors. It's not just nearest neighbor. But in 2-dimensional or 3-dimensional materials, there's a effect called Coulomb. It's called Coulomb screening. So basically, even though the electrons have Coulomb interaction, but because there are positively charged ions around them, the Coulomb interaction is actually screened. At the end of the day, you get something that is interaction that is decaying exponentially with distance. So effectively, you can actually treat the interactions between the electrons as nearest neighbor to a very good level of approximation. But in low dimensions in 1D and 2D, the Coulomb screening effect is actually not very strong. And here you might actually need to consider these long-range interactions. Question, Bauer?
For that screening effect, essentially like the particles at the lattice are coupling with the positive, like your Coulomb.
Yeah, there are also positive charged ions on the lattice,
okay. And
and that somehow just screens this Coulomb interaction.
Okay.
Yeah, it's kind of similar to the electromagnetic screening effect.
Okay.
So to a good approximation, especially for 3-dimensional materials, you can pretty much treat this interaction as just this density-density interaction as just between the neighbors. You might ask for bosons why we don't include that term. In principle, that term also exists. But you can also pretend that the on-site interaction is like the 0th order term, right? And then if you go to the next order, it will be the nearest neighbor interaction. For fermions, we don't have the 0th order term because the two particles can be at the same site. And it's not hard to believe that the particles, if they're on the same side, the interaction is the strongest, right? When they're separated, the interactions gets weaker and weaker. Okay, so this is called the Fermi-Hubbard model. And this model is unfortunately very hard to solve. So I won't even talk about the phases. It's actually much more complicated. You will get a superconducting phase. You're also going to get kind of like a model insulator phase, but it's more complicated. And this one actually is believed to explain high temperature superconductor. And so far, I don't think people have actually simulated this model very well. I talk about there's a big DARPA OLE project dedicated to this, but it's more complicated because for the fermions, especially if you want to simulate the superconducting material, you also have to include the spin degree of freedom. And here I'm ignoring the spin degree of freedom. But for the fermions, that's actually very important because you can actually have two fermions on the same side if they have different spin orientation. So we're not going to talk about that in this course, but this is actually believed to explain superconducting models. And hopefully by playing around with this model, you may be able to get a superconducting material at room temperature. But the underlying model is just as simple as this. Okay, so now we can talk about sort of a more general case. So previously we just talked about the position basis. So what about an arbitrary basis? Right, so we can use an arbitrary basis. We can still just use this phi L here for the single particle. And then how do we actually represent this potential energy here? Actually, this V here, we can write it as a sum of four, basically it's a quadruple sum. I'm going to explain this expression just in a moment. So this particular order here is kind of similar to the order we just talked about, right? Here we have, CX dagger, CX prime dagger, CX prime, CX. And here we have CL dagger, CL prime, CM prime, CM. It's kind of in a similar ordered fashion. So here you can see that we have more summations just because this interaction energy is not necessarily diagonal. So previously, when we are talking about the position basis, we actually find that this part is actually diagonal. You just get NX and NX prime. And here, if you choose a basis that makes your interaction energy not diagonal, and then you have to look at the matrix element. So this is actually the matrix element of the two-particle operator V. Right, so suppose you have a two-particle interaction energy, we can just call it V, and that is an operator that lives in a two-particle Hilbert space, right? So you can pick any two particle, and then if you write the V there, it's going to be basically living in that two-particle Hilbert space. And then what we need to do is to write this V as a matrix in the two-particle Hilbert space, and the basis is exactly given by this, by these things, right? So for a single particle is given by this. You have two particles, then the basis is going to be given by phi L prime, right? So this is also just a tensor product of phi L and phi L prime. And the L and L prime are independent, so which is the reason why this can span the full two-particle Hilbert space. And because it's a matrix element, the rho and the Collin index can be different. So here the rho index is given by the combination of L and L prime, and the Collin index is given by the combination of M and M prime, right? The other way to write this is just going to be a matrix given by L prime and M prime, right? It's very similar to how we represent a single particle operator as just this ALL prime, right? And now you have a two-particle Hilbert space, so the rho and Collin index are actually given by basically two quantum numbers.
So,
Yep.
is that a four-dimensional tensor, or is it still a 2D matrix?
It depends on how you look at it. You can actually glue the two indices into like one big index, right? And then it still becomes a matrix.
Okay.
Yeah, you don't necessarily need to think about it as a tensor. You're right. Technically, it's a rank 4 tensor because you have 4 different indices. But usually, we just glue 2 of them into one big index,
Okay.
And then it just becomes a standard matrix. And usually, we never need to represent this whole thing out. Yeah, question.
What's the difference between L and L prime and
L and L prime, the basis state for these two particles individually, right? Because we're talking about the basis state for two particles, and each one of these can be in a different basis state. So that's why we have a phi L and a phi L prime, right? Like think about 2 qubit, right? So you have a 0 and 1 for the first qubit, and you have 0 and 1 for the second qubit. And it's like your L can be equal to 0 or 1, and your L prime can also be equal to 0 or 1, right? And they are independent. So that's exactly what we're talking here, right? If you really have qubits, then each of these 4 indexes is going to be either 0 and 1, and then you are going to have basically 16 combinations, right? So it's going to be a 4 by 4 matrix in this case. Okay, so this part I don't want to explain it again. It's kind of a generalization of what we get from that position basis. You just have more, they're just more different. You still have two annihilation operators on the right and two creation operators on the left. And this particular order makes sure that if the particles are actually on the same side, you don't need to worry about, they have an interaction energy when you have only one particle. Okay, any questions? Okay, so now we can go to the particular basis that is commonly used is the momentum basis. So here, these basis state, we can just use the collection of momentum for a single particle. I'm just going to denote it by the cat of P. So that's basically creating, so basically it's a state where the particle exactly has momentum P. So now if you think about this interaction energy in the second quantization picture, I'm just going to copy this top formula here. So instead of using L and M, I'm going to use P1 and P2. So I'm going to have basically, P1, P2, P1 prime, and P2 prime. So then I'm going to have a matrix element. I can call it P1, P2, and P1 prime, P2 prime. And then I have CP1 dagger, CP2 dagger, CP2 prime, and CP1 prime. So physically, this means I'm removing two particles at position P1 prime and P2 prime, and then I'm creating two particles at position P2 and P1. And then I'm basically summing over all the possible P's here. So this actually represents the interaction energy for two particles for these two particles. So this is kind of similar to this L and M here. I'm just relabeling them to P1, P2, P1 prime, and P2 prime. This is a common basis because typically we want to talk about a system that is translationally invariant, which basically means momentum is a good quantum number because translational invariance basically tells you that momentum is conserved. And because momentum is typically conserved, for example, the Coulomb interaction will conserve the momentum of the total momentum of the particles, then this particular sum here can actually be further reduced because we need to have momentum conservation, and that basically means P1 plus P2 is equal to P1 prime plus P2 prime. Right? This makes intuitive sense because I'm removing two particles with position with a prime and then creating particles with P1 and P2. And then that means the sum of this has to be equal to each other. That's the total momentum of these two particles. And that actually means instead of doing a quadruple sum, I just need to do a triple sum. So I'm actually only summing three independent momentums. So that's a result of momentum conservation. The other way to think about it is suppose we have just Coulomb interaction, then this interaction can redistribute the two particles' momentum, but you can't actually change the sum of the momentum. So that's what's happening. Right, you can redistribute, you can remove two particles at these two momentum and create another pair at different momentum. So the redistribution of these two particle momentum is fine, but you can't change the total momentum. Okay, so in general, yeah, question, yeah.
So between the two notations, in this notation we've got P1, P2, P1 prime, P2
Yeah.
prime. And it's, I guess the way I'm thinking of it is that P1 prime is the initial momentum of particle 1 and P1 is the final momentum of
Yeah,
particle 1?
you can think about this, right? Because I'm
Yeah.
removing a particle with this momentum and creating one here.
Right.
Right.
And then in the other one, we've got LL prime and MM prime,
Yeah.
and I guess
So you're
with
removing a
seeing
particle.
the
Yeah.
ket on the right side, I'm thinking of that as an initial state and that as a final state. So I
Yeah.
guess the prime to prime.
Yeah, it's a little bit different. Yeah, so in this case, it's
Analogy
removing one and M
doesn't-
and creating one and L, or removing one and M prime and creating one and L prime.
Okay.
So the primes don't correspond to each other. But you just look at the general structure here. So you can see these P1, P2 just correspond to the L prime. And then these two primes correspond to the M prime. Yeah.
Okay. and I guess I'm curious as to, is there a particular reasoning for that change in the notation?
It's okay. These are all dummy variables. It
Okay.
doesn't really matter. I can call these any other things. It's just I probably should change the notation a little bit to be more consistent. But these are all dummy variables. You can call these anything you want.
Sure.
Right. So the important physics is actually here. It really depends on what are the particles you're removing and what are particles you are creating, and then you're always getting a matrix element between the particles you are creating and the particles you are removing.
Okay.
So that's a key. Right. Question board.
Yeah,
Yeah.
and correct me if I'm wrong, but at these sites, if we're in a bosonic system, there could be more than one particle. So
Yeah.
like the total momentum across sites is conserved, but we're transferring particles between the two.
So the total momentum between a particular pair of particles is conserved by the interaction. So just to think about it, right? If you have two electrons under just the Coulomb interaction, right, and they have some initial momentum, and then under this interaction, the system is going to evolve, right? And then the two momentum of the particles can actually change, but they can only redistribute, right? The total momentum is conserved, right? So that's what's happening, right? And one way to think about it is you have two electrons that are kind of like colliding, right? They're going. It's called a scattering process, and the momentum is conserved, right? They can come this way, and then they might be bounced back. So that's totally fine, but you can't change the total momentum. We're actually going to deal with this type of interaction probably in the either the next class or the class after the next. So we're going to talk about how to actually further simplify this type of interaction to make it something that we can solve. So if you just have an interaction like this, it's very hard to solve because these are actually concerning the Coulomb interaction of electrons. And usually you can't solve a system of interacting electrons. It's a very hard problem, especially if you have many of them. And then you need to make some approximations. This is kind of what we said back in the, I think in the third class. You can make different ansatz. For example, you can make a mean field ansatz. In some cases that works well, but in other cases it doesn't work. And the particular answers we're going to make later on to solve this type of interaction is called the Boglev approximation. We're going to come to that later. I also want to mention for some sort of more exotic system like this 2D fractional quantum Hall effect, there are more exotic ansatz try to deal with electron interactions like this. For example, one famous one is called the Laughlin wave function. If we have time, we might want to go into that. So this is for electrons in 2D, and they have Coulomb interactions just like this. And there's no way you can find, for example, the ground state of the wave function analytically. It's just too complicated. Even numerically, it's a hard problem. Laughlin basically makes a guess on this wave function. It takes a very particular form. If you have time, we can look at the details. But just that guess, and then once he solved this ground state, and he actually agrees very well with the experimental measurement. And he actually got the Nobel Prize just for this. Just making a guess of the wave function. It's actually a big deal. And it requires some very smart insight, some very deep insight about the system. Like, you have to guess it in the right form. And it's actually quite remarkable. All right, so that is for how we represent two particle interactions. So now we want to go back a little bit and forget about these interactions and just look at, in the absence of interaction, how we can actually solve a Hamiltonian. When solving it, we actually mean that we can find all the eigenvalues and eigenvectors or eigenstate of this many-body Hamiltonian. Exactly. So here we're going to talk about non-interacting particles on a lattice. And this can be either bosons or fermions. We're going to first treat them in the same way and then talk about the difference of the two. And this is actually one of the most important techniques you are going to learn in this class. A lot of cases, the actual calculation you can do, especially analytical calculations, which also means calculations that can be done for infinitely large system size. If it's analytical, usually it doesn't really matter how many particles you have. It's just your expression has a dependence on the number of particles. So if you don't want to resort to numerical calculations, which are largely limited to maybe 10 or 20 qubits, then you have to learn how to do things analytically. And this is pretty much, I would say, maybe 80% of the things you can do. So it's for non-interacting bosons or fermions on the lattice. And in this case, since they are non-interacting, basically goes back to what we said in the previous class. The Hamiltonian will always take the form of this, right? Because if you don't have interaction, then we're only looking at basically a single particle operator, right? So there's no interaction. So then the Hamiltonian should just exactly be given by this quadratic form. It doesn't necessarily need to be diagonal, but it has to be given by this form. And generally, because we are considering the lattice, we can use we can choose the lattice basis, which basically we can write this Hamiltonian in the following way. So we have a sum over I not equal to j. We have Tij, ai dagger aj. And then we also have the onside term, mu I, ai dag ai. So this is something we said in the last class. So here these ai dagger basically just creates a particle at lattice site I. And generally the Hamiltonian can be written in this form. So you have the I not equal to j term, you can have some arbitrary coefficient Tij here, and then the second term here is just given by some chemical potential, which physically means the energy you need to add one particle at site I. If you have a translation invariant system, these coefficients could be uniform. You can probably just need one number for it, but the most general form is like this. Okay, so this is the most general Hamiltonian for non-interacting bosons or fermions. So if you ever see a Hamiltonian like this, that basically means you have non-interacting bosons or fermions on the lattice. So you don't have interaction energy, which will give you this quadratic term, but you still have this term, which is called the hopping. Right? You can have a particle hopping from site to site I to site j. This doesn't mean that the particles are interacting, right? Because you can have just one particle in the system, which apparently you can't have any interaction energy, but you can have the particle hopping from the site j to site I. So this is where I call this non-interacting, right? Because even one particle, you can have this hopping process, right? This would work. But for the interaction energy, as we just said, one particle would make it not working, right? It would just go to zero. If you just have one particle, you will never have an interaction energy. Okay, so our goal is to actually find all the eigenenergies and eigenstate of this Hamiltonian. This is a many-body Hamiltonian in the second quantization form. So how do we do this? Because this is quadratic, it's actually not hard to solve this. So the trick is we first change this h, this is a curly h, into this vectorized form. So I call it a dagger and a bold h, and then a. So what does this notation here mean here? So here this a dagger is going to be a row vector made of a1 dagger, a2 dagger, all the way to, say you have n particles and n lattice size, then an dagger. Assuming you have n. And then this vector a here is going to be the Hermitian conjugate of this. Since this is a vector, so when you do Hermitian conjugate, the row vector becomes a Cartan vector. So this becomes a1, a2, all the way to an. It's just a Cartan vector made of these a's. So these row and Cartan vectors has nothing to do with like the matrix representation of the operators. This is just like a convenient way I write this Hamiltonian, the sum here. And then this h here, this bold h here, is just going to be this Tij matrix. So it's basically, so we have the Tij matrix on the off diagonal, for example, T12, T13, you know, and so on. On the diagonal, I will have the mu's. So this is my mu1, mu2, and so on. So this is my T21, right? So I basically just, the Tij is already a matrix, but it doesn't have any diagonal term. The diagonal term, I use the mu's. So it's basically going to make a matrix, right? And it's not hard to see that if we do this row vector multiplied by a matrix multiplied by a Cartan vector, I'm actually going to get a scalar. right? And that scalar is exactly this sum. So it's just a convenient way to write this top equation. Here I have a sum, and then here I just want to write it as a matrix. And the matrix elements are actually, the A's are actually given by operators. It's just a convenient way to write it. Yeah, question, Connor.
So, that vector, A vector,
Yeah.
each of those are just numbers, or just scalars?
You mean the elements of the vectors are actually operators?
They are operators.
They are actually operators. Yeah. This is not the matrix representation for operators. This is just a convenient way to write this Hamiltonian on the top to something that is more compact. It's nothing than that, right? So it's just a compact way to write the Hamiltonian. Right? So if you don't see this, I can actually give you an example. Right? So suppose I have a Hamiltonian, the top one. So it's given by A1 dagger A2. Suppose I just have two lattice sides. A2 dagger A1 plus A1 dagger A1 minus A2 dagger A2. Right? So this is just a special case of this underlined Hamiltonian here. Right? I only have two sides. Right? So this basically means my T12 is equal to 1, my T21 is equal to 1, and then my mu1 is equal to 1, and my mu2 is equal to minus 1. Right? So corresponding to that one. Right? I'm just going to highlight this equation. Right? It's just a special case of this. Okay, so now let's see whether we can write this in the more compact form. So I'm going to define my A dagger as just A1 dagger and A2 dagger, and my A as A1 and A2. Right, and then I have a Hamiltonian matrix, the bold H here, that is given by this particular matrix, so it's going to be 1, 1, 1, minus 1, right? Because I'm basically writing the T's here, and the mu's on the diagonal. Right, and then we can just try to do this matrix multiplication based on this. So I will have A1 dagger, A2 dagger, and then I have 1, 1, 1, minus 1, and then A1, A2. And you can do this multiplication, it will directly give you this equation. It's not very hard to see. Right? I don't think I need time to expand this. It's a pretty simple exercise. It's just a compact way to write this Hamiltonian. Okay, so why do we need to do this? And the reason is, once you write this Hamiltonian, this quadratic Hamiltonian in this matrix form, you can actually diagonalize the matrix. So that's the key here. So, so we can basically diagonalize. We can diagonalize this matrix H here. And once you diagonalize this bold matrix H here, at the end of the day, it actually allows you to just solve the eigenvalues, the whole eigenspectrum, energy spectrum of the Hamiltonian. So this H here is going to be a Hermitian matrix, right? Because it's actually related to the fact that this curly H here is Hermitian. So this H has to be Hermitian. This matrix here has to be Hermitian. And because of that, you can always diagonalize it. Suppose we have some unitary matrix U. We have U dagger H and U. Suppose that diagonalize this matrix to some diagonal matrix D here, which is a standard diagonalization we perform. So once we do that, I can rewrite this curly H using this diagonalization, right? Because of this, then I can just invert this equation. I can get my H that is equal to U D U dagger. I can invert this equation because the U inverse is just equal to U dagger. So I can basically just multiply this equation on the left by U and then on the right by U dagger. So we exactly get this. So once I do that, then this form is going to be changed a little bit. So this is going to become A dagger U, and then D, U dagger A. So U, D, and U dagger, they're all matrices, but these are just n by n matrices. So this is basically n by n. So all these matrices are n by n, same as the Hamiltonian. So in this case, I have a 2 by 2 in this simple example. So I get to this form, right? And now I can actually redefine these ones. I can call this a new vector. I can call this C, dagger, and then D, and this becomes C. So basically, U dagger times A is going to give my C, and then A dagger times U is going to give me the C dagger. So what do they actually look like? This again is a matrix matrix vector multiplication. So you look at my C here, right? My A is made of these A1, A2, and so on, right? So this is my A, right? So this is my A here. I'm going to do a matrix vector multiplication. So what I'm going to get is that each of the matrix element will have a sum here. So this one will be a sum over, so I'm not going to write each element. I'm just going to write, so suppose I have a matrix element called CK, then this CK here will be a sum over I, and then have UKI dagger times AI. Right, so just because I'm doing a matrix vector multiplication, and then the case element of this vector is going to be given by this. This is linear algebra. This is how you perform a matrix times a vector. It's going to be a sum given by that. This is UKI. It's a case, row, and i's column. And because there's a U dagger here, this is the case row i's column of the matrix U dagger times AI. And then similarly for CK dagger, you can just take the Hermitian conjugate of this equation, and this becomes UIK AI. And because it's a unitary matrix, when the U dagger is equal to U transpose times Hermitian complex conjugate. So these two are exactly complex conjugate of each other.
You get dagger on the AI and also on
Oh, sorry, yeah, there's a dagger on the AI. You're right. So that's basically this transformation, and then you can simplify this to this, right? And because D is a diagonal matrix, so once you are when you are multiplying a row and a column vector on both sides of the diagonal matrix, you basically just get a simple sum that is equal to sum over K. I can call this epsilon K CK dagger CK, where epsilon K are the diagonal matrix element of D, so it's just the eigenvalues. Right, so I can diagonalize this. So this is going to give me a sum over just CK dagger CK because it's diagonal. The matrix in the middle is diagonal. So we only get the row and column index to be the same. Okay, so this is nice, right? So this one is just the sum over K, epsilon K, NK, right? And that's exactly what we're familiar with, right? We have basically, NK particles in the eigenstate epsilon K. So in this case, it's a Hamiltonian that we can easily solve its energy spectrum because it's diagonalized. Right. If you want to find the eigenstates, is just given by the many-body Fock state. Right? So the eigenstates are just given by N1, N2, and so on. And each of this basically means it's, basically N1 particles in the state created by CK dagger. So now we basically change the basis. So instead of using the original lattice basis, we use this CK dagger, right? So in the particles created by CK dagger, then where the eigenstates are just given by this many-body Fock basis state. And we're going to talk about what the K actually means later on. It turns out that the K in this case actually just means the lattice momentum. So it's kind of related to momentum. But before that, I want to first give you a quick exercise here. Just take this example Hamiltonian we just talked about. So we want to diagonalize this into, I'm going to use a different color here, epsilon 1. So we want to diagonalize into this. And your goal is to find the value of epsilon 1 and epsilon 2 based on this. The thing you need to do is basically diagonalize this Hamiltonian and find its eigenvalues. As long as you can find the eigenvalues of the H, you can basically find the value of epsilon 1 and epsilon 2. So I want to give you just 2 minutes to work on this. Yeah, question board.
So this diagonalization of H
Uh-huh.
with the unitary matrices, that's from my understanding, is a unitary diagonalization, and that's only true for specific variance of H? Like there has to be some conditions on H.
As long as H is Hermitian, you can diagonalize.
Okay, so
So
we're
every Hermitian matrix can be diagonalized. That's
Okay.
just from linear algebra.
right.
Yeah.
So is that always the case that
Yeah.
our H is going to be Hermitian?
H has to be Hermitian because it's a Hamiltonian.
Okay.
Yeah, it has to be Hermitian.
Okay.
Yeah. Yeah, every physical observable is Hermitian. Hopefully everyone can solve the eigenvalues for a 2x2 matrix. If not, you can make a guess. It's actually not very hard to guess. Okay, anybody who has an answer? Any volunteers can tell me the answer for epsilon 1 and epsilon 2? Anybody? Yeah, what about you?
Plus minus 2.
Plus minus 2, okay. Any other? Plus minus what? Square root of 2, okay. So how many of you get plus minus square root of 2? Okay, good. Yeah, that's an easy exercise for you. Yeah, actually, you don't even need to do any calculations. So the way that I would guess is epsilon 1 plus epsilon 2 has to be equal to the trace of the Hamiltonian, which is 0. And epsilon 1 times epsilon 2 has to be equal to the determinant of the Hamiltonian, which is equal to minus 2, right? And then if you just look at these two equations, you can see that the only solution is one is square root of 2, the other one is minus square root of 2. So that would be my way to solve it. Okay, so in this case, we basically know that there are two eigenvalues given here, and the Hamiltonian is basically given by epsilon 1, 1 plus epsilon 2 and 2. And since n1 and n2 are just non-negative integers, you can easily calculate the eigenenergies of the Hamiltonian, right? You just set n1 and n2 to 0, 1, 2, and so on, and then you just add those with the coefficient of epsilon 1 and epsilon 2, right? So then you basically calculated all the energy eigenstates. Just to summarize, so the eigenstates are given by this, and this is the eigenenergy. So here we have n1 and 2. They can just be 0, 1, 2, and so on, right? And actually, if you have fermions, the only difference here is that we just cannot have anything above 2, right? So the n1 and n2 just can be either 0 and 1. In this case, we actually don't even need to worry about the difference between fermions and bosons. If you look at this entire derivation here, I don't even need to distinguish fermions and bosons, because the only thing I'm doing here is a linear algebra. Right? I do the diagonalization, these are all linear transformation, and I end up with this. It doesn't really matter if I have fermions or bosons. So it's basically the same. Okay, any questions? All right, so I'm going to end the class a little bit earlier today, and because the next class I'm going to start with some new stuff. All right, that's it. Yep.
Matrix that we define Hij, does it need to be real valuable because Dij and Dy are real valuable?
The HIJ can actually be complex. Yeah, it can be complex. But for fermions, there's actually some subtle. Fermions have it can be complex. You just need to be Hermitian.
It's just a weird way to essentially, it's happening. You and UDAC are unitary. Okay. Right. So you're sort of like those guys. But then you're also applying the
rotating into your eyes.
it's sort of how you end up. I think if I work that out, you get the eigenvalue squared. Actually, no. Yes. You get the eigenvalue.
I don't think you have an eigenvalue.
Yeah. And then Kobe brought up, which I thought was like the unitary way, which is like, right now, I'm just waiting.
Paul did a list where it was like you and you like both.
Eigenvalues.
but,
I was curious about, you talked about the column, nearest neighbor fraction, and for 2 dimensions and 3 dimensions, you have a higher power.
that makes sense.
Yeah, especially for 3 dimension, the Coulomb scaling is complete. So the interaction actually is not 1 over r, but it's 1 over r times some exponential decay.
I told you to do
So
more.
it effectively makes it shorter because of the exponential.
I'm not familiar. What's happening?
It's kind of like counterintuitive because I expect that exponential to get like more motion degrees of freedom, but
It's really becomes a screening effect, right? Because you have some positive charge, and it's like the same as the usual screening effect. They basically becomes a cage, right? Electrons in the cage, they don't talk. In 2D, you can think about that one of the dimensions you don't have the positive
I've
charge,
been focusing
so it
on
becomes
research
incomplete.
last few days.
In 1D, it's like very
Chopping away at that. I've been really
are there any
simmering
cases where
about question
you get,
2,
like,
3, and I haven't
degrees of
looked at
freedom
question
where the interactions are
I haven't even looked at
maybe
question
even
3. I just finished the coding for 2, but I don't know like
What do you mean by
the part
random?
3 where it's just asking.
It's like
I
diagonal.
guess if you have some matrix
Yeah, well,
of
it's in, I guess
interactions,
you can infer it from the code.
is there any cases where it would be
That's why I would have
nearest neighbor,
class.
like random between any neighbors?
Usually the interactions won't be, but if you are looking at, for example, the hopping here, you can only, usually it's only nearest neighbor hopping, but the hopping strength could actually vary from side to side because you could have some disorder in the system. Right, because like you add some, in the real material, there's usually a lot of disorder. You have a lot of impurities here and there. It creates disorder. That could also make some of the nearest neighbor interactions, disorder. Right, you don't have long range because of that, but you can have, side variation. Like it's not uniform, like what we assumed here, and that actually gives you a very important physical phenomenon called localization. So if you have disorder in the system, then you will find that generally the dynamics of the system is localized. If the electron is here, then it gets stuck. Right, even if you are like in the superfluid phase, but if you add disorder to those T's, it actually gets stuck. But it's not a Martin state, it's called an Anderson localized phase.
Okay.
So that's actually something also very interesting.
Yeah, I'd like to read about that.
Yeah,
That
yeah.
sounds interesting.
Yeah.
But yeah, thank you.
Yep.
We'll see you tomorrow.
Yep, see
Yeah, I was the one who forgot the
clicker?
clicker,
Okay,
yeah,
yeah,
sorry.
sure. Yeah, I'll do that
I did
afterwards. Name is George, right?
Yes.
Yeah, I
Yes.
know it. Yeah.
Thank you.
Okay. Yeah, hey, Matt.
So for these relatively simple models where we have, non-interacting particles,
Yeah.
we can solve the whole like eigenspectrum.
Yeah, it's like
And-
what I just said here,
Yeah.
right? You can basically find all the eigenstates and
Right.
eigenvalues there, right?
And so we get ground state and excited
Yeah.
states, and we
Yeah.
get
You get every
all of that
eigenstate.
information.
Yeah, you get all that
So,
information.
from what I've seen, kind of looking in the literature, where they're starting to talk about, interacting particles
Yeah.
and real material systems.
Yeah.
Trying to solve for
Uh-huh.
spectra of atoms, or
Uh-huh.
trying to solve for excited states of, simple materials. I haven't seen that done very much.
Yeah, because
So is-
usually for interaction it's much harder to deal with. We'll talk about a few different ways you can do this. So one is called the Bogly-Wolff approximation. So you can, in some cases, you can reduce interactions to something called a pairing term, and that actually happens for superconducting materials as well as for superfluid. So you can do some approximation to deal with it. And the other one is to do field theory. So field theory can also deal with some interactions. But at the end of the day, you also basically just transform it to a non-interacting system. So it's kind of like another way to approximate it. So at the end of the day, it's always transforming to some non-interacting system, I would say.
And so I guess my previous interpretation of why excited states are so hard and getting interactions right is so hard is because they grow exponentially with the number of
Yeah,
particles.
if you're doing it numerically, yes, they grow exponentially, right? Yeah.
And that makes it very hard to solve classically.